Hello, this is Jack Jackson. In this video, we're going to be talking about characteristics of discrete random variables. And this is going to kind of summarize many of the things that we've done in the last several videos in this playlist. So let's just review a little bit here. A discrete random variable, okay? The random variable x takes on finitely many or countably infinite discrete values, okay? The probability density function, PDF, has an output which is a probability, so it's in the interval from 0 to 1 for the output, no matter what you put in for x. It's done in such a way that PDF of k is the probability that x equals k. So the output or y value of the PDF is the probability of that particular x value. So then the graph of the PDF is always given as a bar graph, a vertical bar graph, where the bars have the same width as each other, and the height of the bar above a particular x value, like say x equals k, is the value of the PDF function. In other words, it's the probabilities of that x equals that particular k value. So probabilities equal the bar heights. Okay, probabilities are proportional to bar areas. Let's see, area is width times height. So if you take the area, divide by the width, you're going to get the height, which is the probability. Cumulative density function, CDF, is CDF of a k value is the probability that x is less than or equal to k. And the graph of the CDF is actually a step function. The first part over here on the left is a ray that goes forever to the left at y equals 0, and the last one is a ray going forever to the right at y equals 1. The rest are little line segments. That first ray is going to have an open endpoint on the end, and the one on the right is going to have a closed endpoint on the end. And all these little line segments have closed dots on the left and open dots on the right, but they're horizontal line segments. Okay, and so they make little steps. And the steps occur every time you get to an x value that actually has a probability that's not 0, and the amount of that bar, the height of the bar, is the height of the step, which is just the probability of that particular x, and then it jumps up. So the probability, for example, that x is less than or equal to 5 here is right here. It's the same as the probability that x is less than or equal to 4, okay, which is 0.3. So if you look at the table here, here's the table. Here's the x values. Here's the PDF of x. So there's the PDF table, and the graph is the blue bar graph. And if you ignore the blue and take these x's and these y's, here are the red ones. Those red ones are the values of the CDF at the points where the jumps occur. So you can see what the graph of a PDF and a CDF looks like in a discrete case. And the mean is the expected value of x. It sums up all x's times the PDF of those x's and adds all those up. Okay. The variance is expected value of x minus mu squared. So you take, once you found mu, the mean, you take all the x's minus the mean and square them, multiply them by the probability of that x, and add them all up, and you get the variance. Of course, square root of that is the standard deviation. Now, in the next series of videos coming up, we're going to be examining some specific discrete probability distributions. And there are several situations that come up with discrete probability which lead to certain named families of distributions. And these families of distributions cover many useful applications, and many of the most commonly used applications in probability and statistics. These scenarios are common enough that we have names for these certain situations. So in the next few sections, we will consider the following standard families of discrete distributions in more detail. Section 12 will be discrete uniform distributions. Section 13 will talk about Bernoulli and geometric distributions. In section 14, we'll get to the very important binomial distributions. And 15, hypergeometric distributions. Probably the most important part about discrete distributions is distributions of proportions, and those are based on either binomial or hypergeometric distributions. Proportions are extremely important for us in the study of probability and statistics, and of course most of those are based on actually binomial distributions, so the binomial distribution becomes extremely important. And we'll also talk a little bit about Poisson distributions, and there are others besides these, but these are the main ones we're going to be talking about in this particular playlist.